Hello student, welcome to the Web Optics course. Today we have lecture number 65, and in today's lecture we will going to understand how a polarized light can be analyzed. So we have lecture number 65 today. Before going to understand that how a polarized light can be analyzed, I like to recap what we have done in the last class. That we calculated the this expression for index ellipsoid, and let me write down the equation here. 1 divided by n theta was something like cos a squared theta divided by n naught cos a squared theta divided by n o square, O for ordinary light, and sin squared theta divided by E. E stands for extraordinary light. So if this is the axis along which optic axis is placed, then for ordinary, we know that for ordinary ray we have the index will be equal to all the directions. It should be simply a circle. So all the direction the value will be n0. On the other hand, if I look for extraordinary ray, the index value for extraordinary ray depends on the direction. For example, here if I draw a small ellipse inside this circle, then this small ellipse will be the measure of, suppose this is the direction we are talking about, theta. So this value over this ellipse is the value of n theta, and at this point when theta equal to 0, so at this point you can see theta is equal to 0. So when theta is equal to 0, I have refractive index n, which is essentially function of theta, is equal to theta 0 means this portion will not be there, and cos theta, so it suggests that cos theta is 1 and sin theta is 0. So I can write that 1 divided by, here I should put a square, so 1 divided by n square is n o square. So it is simply n theta is equal to n o. Now we increase the value of the theta, and when theta is equal to pi by 2, then we have here this value, this one, then cos theta will be 0, but sin theta will be pi by 2. So in that case we can have the equation 1 by n square, which is a function of theta. For that theta pi by 2 case, we can get this value is equal to 1 divided by n square. So this value is in E, and this value is NO. For this particular system, you can see that, let me draw here. So, this particular system what we have, that this is the direction of optic axis, this is x and y, this is the x and y direction on the crystal. So, this value is in O and this value is in E. Note that here this value is in O either. So, here NO is greater than NE, that is the refractive index of the ordinary ray is greater than refractive index of the extraordinary ray. So, the velocity of the ordinary ray will be less than velocity of the extraordinary ray. So, this kind of crystal is called the negative crystal. On the other hand, if I have a figure like this, suppose and here this is the direction of optic axis, and we know that along the optic axis the refractive index of the ordinary and extraordinary ray are same. And if I draw a figure like this, then this value is NO, this value is also NO, but this value is NE. So, now NE is greater than NO and velocity of extraordinary ray in that case less than velocity of ordinary ray, and this kind of crystal is called the positive crystal. So, sometimes this difference, whatever the difference we have in the refractive index delta n, which is this quantity, is often referred as the birefringence, the value of the birefringence of the crystal. Birefringence of the crystal. That means if the value of delta n is high, we have high birefringence. If the value is low, we have low birefringence. It just determines the birefringence of the crystal. Well, after that, that was the thing we have done in the last class. After that, we will going to understand how a polarized light can be analyzed. So, to understand these this technique, that how to analyze a polarized light, we need to understand a system called Nicol prism. Nicol prism is essentially an optical device designed from, this is an optical device designed from calcite crystal. Crystal designed from calcite crystal, which is used for the production as well as to analyze the plane polarized light, production and analyze the plane polarized light. So let me draw how this crystal is made. So this is the structure of the crystal. Let me draw it first. Then this is the plane we are interested in. Let me set this plane. So we have a plane that is of our interest. So let me name this crystal A, then B, C, D, E, F, this is G, this is H, and these angles is 78 point degree 5 minute typical angle, and these angles are 101 degree 55 minute, something like this. So now what we do, this is the principal, this plane that is said, it is called the principal plane. So let me draw this principal plane here. So A then this point is C, and this point is H, and this point is F, and AF is the point. If I draw a dotted line through this, this is optic axis, and this angle is 71 degree, this angle is 71 degree, and this angle comes out to be 109 degree. This is the principal plane, that plane we are talking about. Well, after having the principal plane, now what normally we do, we cut this plane in a particular angle, and that is in this way. So, this is the plane we are talking about. And we essentially cut this plane. So that was the dotted one, was the original one. Let me draw it properly. So we cut this thing in such a way that this angle previously was 109 degree. After cutting, this angle becomes 112 degree. This angle previously was 71 degree. Now, after cutting, this angle is now become 68 degrees. So, we cut the principal plane with these angles, and then we use this particular section as a generation, as a generator, as a we use this as a generation of polarized light. So, that we are going to show here. So, what we do here, we cut this plane along the optic axis, this principal plane. So, we have two sections here, one is this, and another section is this. I cut from here actually, and this is my A prime, new A prime, because this is C usual, this is my F prime, and this is H. So, if I go back, what is prime? Let me draw it, because originally this this was originally H, this was A, this was C, and this was F. After cutting that, this become F prime and this become A prime. So, these two new points emerge after cutting this thing, this prism. So, now this is the structure we have, and what we do that this region we glue with a specific glue. There is a reason behind that, and that glue we call Canada balsam. For which the refractive index is 1.550. Well, this is 68 degree, and along this direction we have optic axis. So, I have the ordinary and extraordinary ray, and the refractive index of the ordinary and extraordinary ray should be different. So, this is the structure. So, now what happened if I launch a light here? Let us see a unpolarized light I launch, and an unpolarized light I launch, and when we launch unpolarized light here, both the component will be there perpendicular to the optic axis and parallel to the optic axis. So, one ray which is perpendicular to the optic axis, which is the ordinary ray, will get reflected from this interface, and the reason is the refractive index of the ordinary ray is around 1.658, and now it is launched from high refractive index, and the refractive index of this quantity, which is the glue NB Canada balsam, is 1.550. So, there will be a total internal reflection from this point for ordinary ray. However, for extraordinary ray, it will simply pass through, because the refractive index of E ray, this is E ray, is around 1.486 here. So, for this system we can have NO greater than NB greater than NE. So, I can separate out the ordinary ray and extraordinary ray with this structure, because the total internal reflection will be experienced by ordinary ray only, but the extraordinary ray will simply pass through because his refractive index is less than. There will be refraction obviously, but it will pass through. So, whatever the ray I get here in this side is O ray, which is polarized along a particular direction, and here E ray, which is also polarized with a particular direction. Note that the angle of the incidence of the balsam layer must be greater than the critical angle for which this total internal reflection can take place, and accordingly we need to launch the light. Normally it is around less than 14 degree, so that one can have the condition for this total internal reflection at this particular point. Now we know how to generate the polarized light using this system, this nickel prism. So, if I consider that okay, so I launch a light here, so O ray and E ray will generate here in this way. And here we get this light, and here we get this one. Now, if I place a prism, nickel prism again, which behave like a, so this behave like a polarizer, right? So now I place a nickel prism again, and what happened, the light will pass through without any issue. This light will pass through. So I can get light here. However, for the same system, unpolarized light launched. So this light will go this direction, extraordinary light will pass through, and now we place the nickel prism, but we rotate it such that it looks like this. Make a 90-degree rotation, in fact. So this is a rotated nickel prism. So what happened, for now, for this case, this light will not pass through because it will now behave as ordinary light for this. So no light. So with this simple arrangement, so again this is a polarizer which polarize the light, but nickel prism behave here like an analyzer. Which analyze the light. In this case we can have light, but if I rotate these things, I don't have any light. Well, now the production of different light which we discussed earlier, let me quickly discuss this as well, that the production of how to production of circularly polarized light. So, how we produce circularly polarized light? Exploiting this matrix tool. So, it is a superposition of, we can write down the circularly polarized light, the Jones matrix for this we know, we did it several times, is circularly polarized light. Now, this is a left circularly polarized light. I can write this left circularly polarized light as a combination of linearly polarized light in this way. So, this is a linearly polarized light with X vibration plus, if I introduce a phase here, which we can do by introducing halfway plate, then I can have this is one, and this is a left this is again a linearly polarized light, but Y vibration, and by combining these two, one can generate the linearly circularly polarized light, this left circularly polarized light. In a similar way, the right circularly polarized light I can generate as a combination of two light in this way. Here my phase will be negative pi by 2, and again this is X vibration, this is Y vibration, and the phase difference here to two component is minus pi by 2. So, in this way we can produce left circularly and right circularly polarized light using the linearly polarized light, and also using a structure like nickel prism we can analyze the light, and this is the way we can generate and analyze the polarized light. So, today I do not have much time to discuss more about how to analyze these polarized light. In the next class I am going to discuss that how with different combinations of the light one can generate the polarized light, and also how we can analyze with other system, how we can put the phase difference. I just show that how we put the phase difference, how one can put a systematic phase difference by using a system called babinet compensator. So, that we are going to discuss. With that note, I would like to conclude here. Thank you very much for your attention, and see you in the next class.